Welcome to this video where we unravel the complexities of statistical hypotheses and errors. It might seem a bit overwhelming at first, but we'll break it down step by step to make it clear and understandable. We'll explore what statistical hypotheses are and the types of errors that can occur when testing them. Let's start with statistical hypotheses. In statistics, we often encounter notations like H0, mean A minus mean B equals 0, and H1, mean A minus mean B does not equal 0. These might look intimidating, but they're fundamental to hypothesis testing. Breaking it down further, H0 stands for the null hypothesis. The term null implies nothing or no effect. So the null hypothesis assumes there is no significant difference or relationship. H1 or H alternative represents the alternative hypothesis. This hypothesis proposes that there is a significant difference or relationship, contradicting the null hypothesis. In simpler terms, the null hypothesis says nothing's happening, while the alternative hypothesis says something is happening. So, what's the point of these two hypotheses? Statisticians use them as a framework for testing claims. They set up these hypotheses and then conduct tests to determine which one is more likely to be true. When we calculate a p-value, we're essentially asking how likely is it that we'd see this result if the null hypothesis were true. If the p-value is small, it suggests the null hypothesis is unlikely, and we might favor the alternative hypothesis. The null hypothesis assumes any observed effect is due to random chance, while the alternative hypothesis suggests there's a real cause and effect relationship. Imagine a sales manager, let's call her Amy, who implemented a new sales strategy in December, and sales increased by $10,000 compared to the average December sales over the past 10 years. We can frame this using statistical hypotheses. H0, mean A minus mean B equals 0. H alternative, mean A minus mean B does not equal 0. Here, mean A minus mean B represents the difference between this year's December sales and the average December sales over the past 10 years. If H0, the null hypothesis, is true, the $10,000 increase is just due to random chance. If H alternative is true, Amy's new sales strategy likely had a positive impact. The choice between these two hypotheses depends on the p-value. If the p-value is less than 0.05, we typically reject the null hypothesis and favor the alternative hypothesis. If it's greater than 0.05, we stick with the null hypothesis. So if there's less than a 5% chance that the $10,000 sales increase happened randomly, we'd conclude that Amy's strategy was effective. If the probability is more than 5%, we'd say it was just a random fluctuation. This 5% threshold is crucial in statistical inference. It's important to understand what this 5% actually means. When we conduct research, our conclusions aren't always correct. There are two types of errors we can make. Type 1 error, where we reject the null hypothesis when it's actually true, and type 2 error, where we fail to reject the null hypothesis when it's false. A type 1 error is often considered more serious because claiming an effect exists when it doesn't can lead to misguided decisions, like thinking Amy's sales strategy works when it's not effective. The 5% significance level, alpha, is the probability of making a type 1 error. In other words, by using a p-value of 0.05, we are accepting that there is up to a 5% chance that we will incorrectly reject the null hypothesis. This means we are willing to conclude that there is an effect when there isn't one in reality, 5% of the time. When you're first learning statistics, it's okay to think of the p-value as simply the probability of an event occurring by chance. However, it's good to be aware of the more precise definition. The probability gives a threshold of acceptable false positives in the statistical test.